This is AP Calculus BC, and in this video what we're going to do is talk about section 5.4, which is starting to transition from what we were talking about before with indefinite integrals into the idea of a definite integral. And what we're really going to focus on here is what we call rectangular approximation. Now, the title of this section is the definition of area as a limit, and then it also says sigma notation. But the main idea behind what is covered in this section is going to be rectangular approximation and different ways we can write out those rectangular approximations. So to start with here, what we have is a graph that is a velocity graph. And what we're trying to think about is, if I wanted to find the distance from a velocity graph, the distance traveled, how could I do that? So if you think about a velocity function that's constant, like let's say, for instance, we're driving 75 miles an hour for 2 hours. Well, it's pretty easy to calculate from that if I'm driving at a constant velocity of 75 miles an hour for 2 hours, I'm going to travel 150 miles. So all we're really doing there is using that constant rate multiplying by time. Well, if you were to think about that graphically, what you would have on your velocity graph would just be a horizontal line. And then if I were to multiply by the amount of time that was traveled, what I would really be looking at on the velocity graph would be the area of a rectangle. So what we're looking at here with this velocity graph is the same idea, but now we have a velocity that's not constant. We have a velocity that's varying. So if I were to try to find the distance traveled from this velocity graph, it would be much more difficult to do because I don't have a rectangle anymore. I have an irregularly shaped region here that I'm trying to find the area of. So what we have to do then is we have to go about it in a little bit different way. And this is where we get into the idea of an integral. What we're going to do is take this interval that goes from A to B, and we're going to break it into a bunch of smaller subintervals. And you can see with these subintervals, when we start trying to approximate this, I can more easily try to approximate areas of these small regions as opposed to trying to deal with the whole region all at once. And what we're going to do is essentially treat these regions as rectangles. And there's different ways that we can go about this. But you can see with the rectangles, they give me a good rough approximation of the area of each one of those subintervals. So that's sort of the idea of what we're getting at today when we start talking about definite integrals. Now, there's some different ways that we can do this. When we start trying to find the area underneath a curve, that's what a definite integral really can be represented by. And the way that we're going to calculate that is by using some approximation methods. Now, what we have here is an example where we're looking at a velocity function. We have velocity is t squared, and it says where's the particle at time is equal to 3. Notice it says the particle starts at x is 0. So if I want to know where I am at time is 3, I just need to know, since this is a positive velocity, what was the distance traveled between time 0 and time 3? Well, take a look at these three graphs. So the one on the left, you can see that they've broken this into 6 subintervals. So I had a time interval from 0 to 3. Each one of these time intervals has a length of, or a width of 0.5. And then to find the height of each one of these rectangles, what they're doing is they're taking the height or the function value to represent the height at each one of these left endpoints of the subinterval. So you can see all these left endpoints are going to give me the heights of the rectangles. So this is called a left-hand rectangular approximation method. So when I do a left-hand rectangular approximation method, that's all I'm really doing. I'm getting the area of 6 rectangles in this case, and I'm going to add them all together, and I'm going to say that's approximately equal to the area under the curve. Now, obviously, in this case, I'm severely underestimating the actual area underneath the curve, but it will give me a good rough idea of what that area is going to be. Now, down below here, I've actually shown you what would happen if we were to add these together. So think about the base of each one of these rectangles. The base would just be the width of the subinterval. It's 1/2 of a unit, and the height is going to be the function value at each one of those left endpoints. So you can see the left endpoint between 0 and 1/2 is at 0. So I plug 0 into the velocity function, and 0 squared is 0. Here I've got the left endpoint when I'm on the interval from 1/2 to 1. 1/2 squared would be the height. And then all the way through, notice the last one here, we're on the subinterval that goes from 2.5 to 3. So we're going to use the function value on the left side there. So that's the idea behind this. Now, again, we know this is an underestimate, but the main idea is what happens when we add more rectangles to this. That's really what we're going to be getting at. So there's 3 ways we can do this. And just really quickly, just to mention this, down below here, I included a little bit of information for you about how to do these things on the calculator. This is not something you have to know how to do, but if you're interested, you can play around with the lists in our TI-84 calculators, and you can use those to do a rectangular approximation. In this case, we're setting up the values that are going to make the pattern that you see in that summation that I've written out. Okay, so left-hand rectangular approximation method was one of the methods we could use. Let's switch over here to the one on the right. So on this one, if you notice, we have 6 subintervals again, but this time the height of each one of these rectangles, and I'm on the wrong triangle here, the height of each one of these rectangles is actually going to be determined by the right side of each subinterval. So you can see the right side of each subinterval is approximately the function value for each one of the heights of those rectangles. So it's the same idea, but this time, since we're using the right-hand side of each subinterval, we call this the right-hand rectangular approximation method. Okay, so on this method, everything looks the same in terms of the calculation, and this is the calculation that I'm referring to. So if I'm going to find the sum of those 6 rectangles, all I'm going to do is take the function value at the right side of each subinterval. Notice the base is always the same, right? The base is 1/2. So every one of those rectangles has a width of 1/2. The height is what changes. So this time on the first subinterval, I'm going from 0 to 1/2. The right side of that subinterval is 1/2, so that's where I'm going to get my function value. And then the next subinterval goes from 1/2 to 1. That's where this 1 came from, all the way till I get to the last subinterval, which goes from 2.5 to 3. So notice that one ended at 3 this time because that's the right side of the last subinterval. Okay, so when we are calculating these, there's one more method we can use, and that's the one that's in the middle here. And on this middle one, you can see these function values are being determined by the midpoint of each one of these subintervals. So when I go through and I find the height of each rectangle, I'm saying, okay, for instance, on the first subinterval, it goes from 0 to 1/2. What's the function value at 1/4? That's going to be the height of my rectangle. When I go from 1/2 to 1, what's the function value at 3/4? That's going to be the height of my rectangle. So that's the process that we're going to follow. This is called the midpoint rectangular approximation method. And these acronyms that I'm writing, that's usually how we refer to these things as opposed to writing all of that out. Okay, so with the calculation, you can see that's done over here. And like I mentioned, with the heights of each one of these rectangles, you can see the midpoint between 0 and 1/2 is 1/4. The midpoint between 1/2 and 1 would be 3/4, all the way till we get to the midpoint of 2.5 and 3 would be 2.75 or 2 3/4. Okay, so all of these are going to give me slightly different values. What matters though is, with my rectangular approximation, I can use more and more subintervals, and it's going to get me a more and more accurate result. So you can think about, for instance, on each one of these graphs, you can see how there's a little bit of error involved in all of the methods. There's either missing area or extra area or a combination of the two. So there's definitely error in all 3 methods. For this particular case, it looks like midpoint is probably the most accurate when we have 6 subintervals. But the reality is, as I increase the number of subintervals, and this is some different notation that we can use here. See how this says L sub n? That's saying we're using a left-hand approximation with n subintervals, or a right-hand approximation with n subintervals, or a midpoint approximation with n subintervals. As that number of subintervals gets higher and higher and higher and gets infinitely large, all 3 of these methods are going to converge to the same value. So eventually, they're all going to give me the exact area underneath that curve, which is exactly equal to 9. And so for today, that's really what we're going to do, is just focus on rectangular approximations. Now, there are ways that we can solve this out without doing the approximations, but what we're trying to get right now is, we're trying to get the idea behind what's actually happening when we solve a definite integral. Okay, so let's take a look at a couple of examples. This is a fairly easy process. It says the speed of a runner increased steadily the first 3 seconds of a race. Her speed at half-second intervals is given in the table below. Find the lower and upper estimates for the distance that she traveled during these 3 seconds. Okay, so take a look at the values that we have in this table. You can see the time values are evenly spaced, and you can see that the velocity values are increasing throughout this entire time interval. So if I'm thinking about a lower estimate, I want to be using the subinterval method that is going to give me the lowest value on each subinterval, which clearly, since these are increasing values, that would be a left-hand approximation. So I'm going to do my lower estimate here. So the distance traveled can be approximated by this. Now, what I can do here, rather than writing out each rectangle separately, I know the base of each one of my rectangles is going to be 1/2. If I'm thinking about a time axis here, each one of these subintervals has a length of 1/2. So I'm going to factor out that 1/2. And now, knowing that I'm going to create a bunch of rectangles, I can just add all of the heights of my rectangles, and that would be a shorthand version of what I had written before when we were dealing with that velocity is t squared function. Okay, so for the first subinterval, I'm looking at this subinterval between 0 and 0.5. And you can see I have 2 points to deal with there, but I want to choose the one on the left-hand side, which would be 0. Then I get to this next subinterval from 0.5 to 1. You can see the left-hand side of that would be 6.2. And I'm just going to go through all of these, 10.8, 14.9, 18.1, and 19.4. Now, notice I'm not going to use this last value of 20.2 because I'm using subintervals that go from, or that are a length of half a unit. So my last subinterval from 2.5 to 3, I'm only going to use the value at 19.4. So I'm essentially ignoring the point at 20.2 using this method, or the point at time is 3 using this method. So my distance approximation using this method would be about 34.7 feet. Okay, they also asked us for an upper approximation. Well, for the upper approximation, it's going to be a similar setup. We know we're using a bunch of rectangles that have a base of 1/2. The difference now is for the heights, I'm going to use the right side of each subinterval. So instead of starting at 0, I'm going to start at 6.2, and then I'm going to use all these values to create my rectangles. So I'm going to go all the way out this time to the last term, because when I'm on that last subinterval between 2.5 and 3, my height of my rectangle would be 20.2. And when we multiply all that out, we're going to end up with about 44.8 feet. Now, the reality is, neither one of those answers is probably exactly correct. But what we can say, assuming that our velocity is increasing throughout this interval as it appears to be, most likely our actual distance travel is somewhere between 34.7 and 44.8 feet, because we had an estimate that's definitely on the low side and we have an estimate that's definitely on the high side. So most likely the distance travel is going to be somewhere between that. Okay, so here's another example of the same type of thing, just a simple application. It says the velocity graph of a braking car is shown. Use it to estimate the distance traveled by the car while the brakes are applied. Okay, so this time we're not given a table of values. So the first thing we have to think about on a problem like this is what method do we want to use and how many subintervals do we want to use? Since I don't have exact values to work off of, I want to get as accurate of a solution as I can, but I need to decide which method's going to work the best in this case. So the first thing is, it looks like 6 subintervals is probably the most reasonable number of subintervals I could choose, because I've got this grid that's separated on 1 unit intervals. So I'm going to use 6 subintervals. So when I approximate the distance here, I know the length of each subinterval is 1. That's the base of each rectangle. Now, when I'm finding the height, I have to decide what method I want to use. If I use a left-hand approximation, it's clear I'm going to overestimate in this case because this is a decreasing function. If I use a right-hand approximation, I'm going to underestimate. So since I have the option to do this, I'm actually just going to do a midpoint approximation. So for each one of these subintervals, I'm going to approximate the height at the midpoint of each subinterval. So that would create my 6 rectangles here. And then I just have to approximate what are the values at the midpoint of each one of those. So the first one I'm going to say is roughly 54. The next one is somewhere around 40. The next one I would say is about 27. And then maybe around 18. Then it looks like we're about 10. And then the last subinterval looks like it's pretty low, maybe somewhere around 5. Now remember, these are just approximations. So if you did this on your own and you got slightly different numbers, that's totally fine. We're just approximating from the graph. We don't know what this function is. So we're estimating that the distance traveled here would be about 154 feet. So the important part of this is I tried to minimize the amount of error by using a midpoint approximation, which I could do in this case. And the second thing is I chose 6 subintervals because that was sort of the natural progression that I had in terms of the number of units that are shown on this graph. It looks like it goes on 1 unit intervals. Okay, so when you do your homework, you're going to have a lot of these types of questions. When you're dealing with a function, you can really use any of the 3 methods. It doesn't really matter. But when we start getting into working these types of questions off of tables, we don't really use midpoint approximations when we work off of tables. And let me just explain why here. Let's say on this previous problem where we had a table of values and it said the speed of the runner increasing steadily. Well, if I want to do a midpoint approximation, I can't use a time interval from 0 to 0.5 because I don't know the velocity at the midpoint of that time interval. So what I have to do instead is I have to make my time interval twice as large, and then I can use a midpoint that I actually know a value for. But if you notice here, what ends up happening, because I'm doing that, so now my next subinterval is going to go from, let's see, let me draw this in a little bit different way. We'll go from 0 to 1, and then the next subinterval would go from 1 to 2, and then the next one would go from 2 to 3. So the only values I'm going to end up looking at are going to be these 3 values. And if you notice in this table, there are 7 data points. So by using a midpoint approximation, I'm essentially disregarding more than half of my data. So a midpoint approximation could be wildly inaccurate because there could be really important things happening with my function at these midpoints or outside of these midpoints that I'm not accounting for. So as a general rule, we're never going to use midpoint approximations when we're doing rectangular approximations with data sets, just because we're disregarding so much of the data. So try to keep that in mind when you're working through some of these application problems. All right, so the last application problem that we have here has to do with approximating the volume of the nose cone of a rocket. And you can see that to create this graph, essentially what we have is a paraboloid. That's a 3-dimensional object that's sort of got, if you were to take a cross-section of it, you can see that if we were to cut this along the x-axis, instead of the way that they're cut this way, we would see that we would have a parabolic cross-section. But what we're going to do here is we're going to approximate the volume of this by taking slices vertically. When we take slices vertically, if we were to look at any point along there and we cut it and then we looked at the base of what we had cut, we would see a circle. So what we're going to do then is we're going to approximate this paraboloid by using cylinders. And you can see they've drawn in the cylinders here and they've given us a rough idea of what they want us to do. We're going to approximate this with 5 subintervals using left endpoints. Now, keep in mind here, we're still doing the same idea as a rectangular approximation, but now we're actually approximating volume. So I still want to keep the same thought process, but I have to think about this in a slightly different way because this is the volume of a cylinder, right? Each one of these is going to be a cylinder. Well, a cylinder has a volume of pi r squared times the height. Okay, so I know the height is always going to be 1. So when I'm evaluating my overall volume and I approximate it with these cylinders, remember I have 5 cylinders, I know that I've got pi in every one of these cylinders that I'm using. I've got a height of 1 in every one of these cylinders. And then what I'm going to put inside My parentheses or my brackets this time are all of my radii squared. First subinterval goes from 0 to 1. So the left-hand side of that is going to give me the square root of 0. The next one goes from 1 to 2. So I'm going to have square root of 1 squared. Then from 2 to 3 is going to give me square root of 2 squared, and so on, all the way until I get to that last subinterval, which would be at the interval between 4 and 5, so square root of 4 squared. So once I finish all that out, this is going to be a volume of approximately 10 pi. Now, just like we saw before, is that really accurate? I mean, clearly it's not. I don't have any volume accounted for in this end piece of this paraboloid, and I've got all this missing volume here in these regions. But it gives me a good rough approximation. I would consider that to be an underestimate. I could do the same thing with a right-hand approximation, get an overestimate, and I could average those two out. Or I could do a midpoint approximation and get a pretty decent one-time calculation that would give me a pretty good feel for what the volume of that paraboloid would be. So we've got some options, but the main idea is just because we're dealing with volumes, it doesn't mean that anything really changes. It just means that we're using the same idea and now applying this in a slightly different situation. All right, the last thing that I want to talk about here is just another method we can use for writing out these rectangular approximations that's a little bit more concise as opposed to writing out those long summations where we're writing them out term by term. What we're going to do is just talk about a way that we can write these using a sigma notation. Sigma notation you guys have seen before in pre-calculus, and so this is just a really quick review of how sigma notation works. And then what we'll do is we'll talk about how we can use this when we're doing our left hand, our right hand, or our midpoint approximations. There's not really a lot of information about doing this with sigma notation in your textbook, so use these notes really as your tool in terms of reference material if you need to go back and review this. So first of all, for sigma notation, remember when we have this sigma notation, essentially what this is saying is we're going to add up all of the terms here. This is called the index number. We're going to go from the k equals 1 term to the k equals 6 term using the formula 3k plus 2. So when we do that in this case, when I plug in k as 1 into this equation, I'm going to get 3 plus 2, which is 5. When I plug in 2, I get 8, and so on. And then I would get 11, and then 14, and 17, and then 20. So that would give me a total of 75. So again, you've seen sigma notation before, but just as a quick reminder of how it works. So this is one we could easily figure out. There are 10 terms here because it starts with the first term goes to the 10th term. We're just going to add up the number 5 10 times, so we're going to get 50 for this one. And then for the last one, if you want to go through and try that one on your own, you would see that you get a sum of 130. Okay, so it says write the following series in sigma notation. So this is really what we're going to be trying to do with these problems that we look at. We're going to look at the patterns. We're going to try to figure out how to write these long rectangular approximations. We're going to write them in a more concise form. So with this sigma notation, you can use whatever letter you want as your index. I usually use N, but you'll see K or I or J. You'll see a lot of different things used for that index number. But if you notice this pattern here, it looks like we're going from the first term to the 11th term. So there's going to be 11 terms there, and I'm following the formula here, 1 over 5n. And then you can see if you were to plug in 1 and then 2 and then 3 and sum up those terms as you go and so on, that's the expression that we are writing in a shorthand notation. Okay, so here's another one. You can see we've got 2 multiplied to all of this. So you can actually factor the 2 out of the summation this time. Just to let you see it a little bit differently, I'm going to use a k this time. So I'm going to say k is equal to 1. And notice that this value is what's changing every time. So it looks like I'm going from 1 to 6. And I've got 7 times some value divided by 6 plus 5. And I usually put the parentheses all the way around so that I can tell that that summation applies to all of that. Okay, so that's just a quick review of how to write those summations. Now, remember what we were doing was rectangular approximations. And when we were doing rectangular approximations, this is essentially what we were doing. Delta x was the subinterval length. And then to find each of those function values, in this case, we're looking at a right-hand notation. We would essentially be going to the right side of the first subinterval all the way till we get to the right side of the last subinterval. Well, this is on an interval starting with a left endpoint of A. So if I'm at my left endpoint of A, if I want to look at what's the height of the first rectangle, I need to go to the end of the first subinterval. And you can see that that's why delta x is added here. And then however many subintervals we have, that's how many times we're going to have to add delta x to get to the last function value at the end of the last subinterval. So you can see each time I'm just adding delta x to get from one term to the next in terms of where do I evaluate the function value. So since we have sort of a pattern for this, as opposed to writing it out now in this long form, we can factor out the delta x like we already did, and then we can write all of these function values that are being summed up. We can write them just as a general rule, f of a plus some number times delta x going from the first subinterval to the nth subinterval. So this is a general setup that we can use to write those summations in a more concise form. All right, so let's take a look at just an example of how this would be done. So in this case, we're looking at the function f of x is x to the negative 1 power, or f of x is equal to 1 over x. Okay, so notice we're looking at the interval from 2 to 4. And what we're going to do is we're just going to write a left hand, a right hand, and a midpoint approximation for this. And the first one we're going to do is a right hand approximation. So the first thing is we have to know how many subintervals we're going to do. Well, with this notation, I can see that I've got this subscript of 6, so I know I'm going to do 6 subintervals. So the first thing I need to know is what's the length of each subinterval? Well, my interval goes from 2 to 4, and I've got 6 subintervals, so each one of those is going to have a length of 1/3. And so essentially we take the left endpoint or the right endpoint minus the left endpoint, and that's the length of our interval divided by n, and that gives us the length of the subinterval. So now we know what delta x is. And remember, just like we looked at there, if we want to know what's the pattern for this, well, every time to find the function values, I'm going to do f of a being the left endpoint, in this case would be 2, plus j times delta x. Each time I add delta x, it gets me to the end of the next subinterval. So the first time I add delta x, I'm at the end of the first subinterval. Another delta x gets me to the end of the second subinterval, and so on. So what we're going to do is come up with a general formula for this. So we know we're going to add a plus j delta x. Well, we know a is 2. We know delta x is 1/3. So that gives me an expression that I'm going to substitute in to my 1 over x formula. So in the end, f of a plus j delta x, I'm plugging all of this in for the x, remember, in that 1 over x rule that we had up here. So that's what's being done to come up with this expression, which then simplifies down into 3 over 6 plus j. So now in the end, rather than writing out this whole long mess of rectangles, I can just write it out as a really concise summation, 1/3 being my delta x times the sum of all the function values that would be the endpoints for all of those subintervals, and that would represent this thing here. Now, that doesn't really make a lot of sense to do when I only have 6 subintervals, but you can imagine if you had, let's say, 100 subintervals or 1,000 or 10,000, I can now easily come up with an expression that represents that long summation. I can write it in a really concise form. Okay, so let's go through the same thing and do this with a left-hand approximation. So with the left-hand approximation, it's very similar to a right-hand approximation. The only difference is when I look at my setup for this, I remember my delta x was 1/3, but this time when I'm thinking about that f of a plus j delta x, well, when I'm at the left endpoint, my first subinterval, the left endpoint would be 0 delta x is added. So I'm going to start at j is 0, and when I'm on that last subinterval, the 6th subinterval, I'm going to be looking at the left side of that, so I'm going to add 5 delta x's when I get to that last subinterval. So notice the difference here. When I was doing a right-hand approximation, I needed to add the first through the 6 delta x's, because at j is 1, that means I'm at the end of the first subinterval. This time at j is 0, that's the left side of the first subinterval. So everything else about this is the same, though. I'm still going to have 3 over 6 plus j. And remember, that's just, if I were to write this out, that's just shorthand for 1/3 times 3/6 plus 3/7 plus 3/8 plus 3/9 plus 3/10 plus 3/11. So again, it's just a shorthand notation to make this a little bit easier. And if I were to add that all up, that's about 0.737. Remember, this is a function that is decreasing in value on this interval, so I would expect the left-hand approximation to be a little bit higher than the right-hand approximation. All right, so the last type that we could do is a midpoint approximation. Well, midpoint approximation is a little more complicated because now we've got to get to the midpoint of each of these subintervals. Remember, we're still dealing with the same function. F of x is equal to 1 over x. So when I'm going to do this notation, you've got to think about this a little bit. Here's my left endpoint. That's what I'm going to plug into my function to evaluate the function value at what point. So the left endpoint plus half of my subinterval length. So notice this j minus 1/2. If I plug in j as 1, that's going to give me half of delta x. If I plug in j as 2, that's going to give me 1.5 delta x's. So the first half delta x gets me here. Let me do that in a different color. First half delta x gets me here. And then I add another delta x to that. And now I'm just adding a delta x each time to get from one point to the next. So that's how that formula is just slightly different. And what's also a little messy here, this is what I've got to plug in to that equation. I've got to plug that into the 1 over x and simplify it down. And it simplifies down with some algebra into 6 over 12 plus 2j minus 1. So once we have that, now to write our summation, well, that's pretty easy to do because the summation is just the shorthand of all of that, and we've already got the formula that we're going to use for the function values. So my midpoint approximation with 6 subintervals, I could write as, let me rewrite that 6. I could rewrite that as 1/3 being my delta x, and now this summation is going to represent all of those function values at the midpoint. J is 1 to 6. And remember, it was f of a plus j minus 1/2 times delta x, but that's simplified into 6 over 12 plus 2j minus 1. And that would give me, if I expanded it out, which we really don't want to do, but I just want to show you what it would have been. This is shorthand for 1/3 of 6/13 plus 6/15 plus 6/17 plus 6/19, 6 over 21, and then 6 over 23. Okay, so in the end, if I were to plug that into the calculator, that's about 0.692. Okay, and again, just to reiterate, I wouldn't really do this if I only had 6 subintervals because I can easily write out this entire summation. But this is more something we would use if we had a very, very large number of subintervals. Then we can just use the pattern, write a simple formula, and we don't have to write out a bunch of terms. Okay, so as far as homework goes, a lot of what you're going to do is going to be in Wiley+, but I did attach a worksheet to this for you. And the main reason I attached the worksheet is because your textbook doesn't really have the types of questions that we were just dealing with. So at a minimum, even if you don't do the entire worksheet, make sure you look at and try questions 11 through 14. So what they're trying to get you to do here is essentially work backwards. So you're starting with the summation. That's the result of the process we were just talking about. And you're trying to work backwards to figure out what the function was. So I want you to try that and see if you can figure those out. You can see that there's also some here where they ask you to write the summation to represent the right-hand approximation or the left-hand approximation. We sort of have a formula to do that using the patterns that I just showed you, so that's pretty straightforward. But if you really know it well, you can do it backwards, which is what 11 through 14 is. So I do have the solutions for this posted in Schoology. Also, if you go to the class calendar, you can get them there. So make sure you, at a minimum, work 11 through 14 and try those.